You think darkness means no light. So if you can't see your own hand, you assume you're not emitting anything. But what if the room is bright, just not for your eyes? Then what does it actually mean to give off light, and what are you doing right now? You've probably said something like, if I can't see myself in the dark, I'm not giving off light. And it feels reasonable, because in your head, light means visible light, the stuff your eyes can catch, the stuff that makes colors. But physics doesn't care what your eyes can catch. So here's the problem we're going to untangle. What does it actually mean to emit light? And why are you absolutely unavoidably emitting photons right now, even if the room is perfectly dark? Because if you get this straight, a bunch of other things suddenly stop being mysterious. Like why a thermal camera can see you through darkness. Like why a hot stove glows red but a warm cup of coffee doesn't. Like why the night sky isn't truly black if you look with the right kind of eyes. And this is the fun part, why light is a much bigger idea than you were taught. Let's start with the everyday picture you've got in your head. In the everyday world, objects are either light sources or not light sources. A lamp is a light source. A rock isn't. A candle emits light. Your hand doesn't. If the electricity goes out, the room goes dark, and you say no light. So you build this rule: if I'm not visible, I'm not emitting light. Now here's the catch. Visibility is not a property of the object. It's a property of the combination. Object plus illumination plus your detector. Your detector in this case is your eye. And your eye is picky, shockingly picky. Your eye detects only a tiny slice of the electromagnetic spectrum, roughly from about 400 nanometers to 700 nanometers in wavelength. That's it, a thin band, a narrow window. Outside that window, your eye is blind, and the universe is not designed around your eye. So when you say there's no light, what you usually mean is there's no light in the tiny band my eye evolved to see at a brightness my brain can notice. That's not the same sentence. Now, what are we even talking about when we say electromagnetic spectrum? Same basic phenomenon. Electromagnetic radiation, just different wavelengths. Radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays. Different labels, same family. Same kind of thing traveling through space. Different color in a deeper sense than your eye can register. Visible light is just the part your biology decided was useful. So the real question becomes, if you're not emitting visible light, are you emitting other wavelengths? And the answer is not maybe. The answer is you can't avoid it, because anything with a temperature above absolute zero emits electromagnetic radiation. Anything. Not because it wants to, not because it's charged up, not because it's special, because it's made of atoms. And atoms at ton-Goer temperature are not sitting still. They're jiggling, colliding, vibrating, accelerating charges back and forth, and accelerating charges radiate. That's the basic physical engine behind what's called blackbody radiation. Now, blackbody is one of those textbook words that makes it sound like we're talking about some exotic object, like a literal black body. No, it's an idealized concept, an object that absorbs and emits radiation as efficiently as possible. Perfect absorber, perfect emitter, a mathematical reference point. Real objects are messier, but many of them behave close enough to a black body for the main point to be true. The spectrum of radiation they emit depends mainly on temperature. Temperature sets the shape of the glow, and here is where your intuition breaks. When you hear glow, you picture visible light, yellow, orange, white hot. But glow just means emitting radiation. The color of the glow might be invisible to you. Take a piece of metal. At room temperature, it's emitting radiation, plenty of it. But almost all of it is infrared, wavelengths longer than visible red. Your eye can't see it. Heat the metal up. Hotter, hotter. At some point it starts to emit enough radiation in the visible band that your eye finally catches it. First it looks dull red, then orange, then yellow, then white. Nothing magical happened at the moment it started glowing. It was always glowing. What happened is the peak of its blackbody spectrum shifted towards shorter wavelengths as the temperature rose, and the visible band finally got a significant share of the radiation. So now put your body into that story. Your body temperature is around 37 degrees Celsius, about 310 Kelvin. Not thousands of degrees, not even hundreds. If you plug that into the basic physics, the peak emission wavelength of a 310 K blackbody sits in the infrared, around 9 or 10 micrometers, way outside visible light. So you are glowing. But you are glowing in infrared. Right now your skin is dumping photons into the room. not a trickle, a steady flood balanced by the energy you gain from the environment and the energy you produce metabolically. You're like a low-temperature star, not bright invisible light, but absolutely bright in thermal radiation. And the room isn't empty of light either, by the way. The walls are emitting infrared. The table is emitting infrared. The air is exchanging energy with everything. The whole room is a soup of radiation being traded back and forth. This is why temperature isn't just a number on a display. It's a physical condition of matter that shows up as motion and radiation. Now, there's a second confusion we need to isolate, because it sneaks in quietly. People imagine that emitting light means producing extra energy, like a flashlight. It consumes chemical energy in a battery, turns it into electromagnetic energy, shoots it out. So they assume if you emit light, you must be using energy to create light. But thermal radiation is not optional production. It's a consequence of having energy in random microscopic motion. If you're warm, that energy has to exist somewhere in the microscopic vibrations and movements of atoms and molecules, and those motions couple to electromagnetic fields and radiate. You don't have to decide to do it. You can't hold it in. And here's the brutal part. If you stopped radiating, you'd stop being warm. You'd cool down fast. Radiating is one of the ways you lose heat. So when you say, I don't emit light, you're accidentally saying, I do not lose heat by radiation, which is false. Demonstrably false. You can measure it. This brings us to the modern magic trick everyone's seen, thermal cameras. A thermal camera is not reading your thoughts. It's not detecting life force. It's not doing some science fiction thing. It's just a camera with a different detector. Your phone camera has sensors designed for visible wavelengths, roughly what your eye sees. A thermal camera has sensors designed for infrared wavelengths, often in a band around 814 micrometers, because that's where room temperature objects radiate strongly. So when you stand in a dark room and a thermal camera sees you clearly, that is not the camera cheating darkness. Darkness to your eyes just means not enough visible photons. To a thermal camera, that same room is bright, not visually bright, thermally bright. Every warm object is broadcasting. You, the chair, the floor, the walls, all of it. And if you want a clean definition for the problem we're solving in this first part, it's this. You confuse light with visible light, and you confuse seeing with emission. Those are two different mistakes. An object can emit light you can't see, and you can see an object without it emitting visible light if it reflects visible light from somewhere else. That second point matters because it's how almost everything you see works. A book doesn't shine in visible light. It reflects the lamp's light. In darkness, it looks like nothing, not because it stopped existing, but because there are no visible photons bouncing into your eyes. But the book is still emitting infrared photons the whole time because it's warm. So the dark room idea is a trap. It makes you think the world goes optically silent. It doesn't. It just goes silent in the one narrow channel your biology listens to. And that's where we'll go next, what the blackbody spectrum actually looks like, why temperature picks the color of your glow, and how many photons your body is throwing out every second, quietly, continuously, like the universe has you permanently on air. So let's make that on-air claim concrete instead of poetic. When physicists say blackbody radiation, we mean something brutally specific. For an object at a given temperature, there is a predictable distribution of electromagnetic radiation it emits at each wavelength. Not a single wavelength, a spread, a whole curve. And the curve has two big features you can hang your intuition on. One, there's a peak, a most common wavelength. Two, the total area under the curve grows fast as temperature increases. That's it. That's the whole story, dressed up in equations and textbooks. Now the peak shifting is the part your intuition actually already knows. You just didn't label it. Heat a poker iron. It goes from not glowing to dull red to orange to white. But what's really happening is, at low temperature, the curve sits mostly in infrared. As temperature rises, the peak slides left toward shorter wavelengths, and the tail of the curve starts spilling into visible light. That sliding is summarized by Wien's displacement law. It's basically hotter means bluer, not blue as in the color name, bluer as in shorter wavelength. Room temperature, peak in the infrared. Sun's surface temperature, about 5,800 K, peak in the visible. That's why daylight exists at all. And now your body about 310 K, peak around 9-10 micrometers, infrared. So yes, you're glowing, but you're glowing in a band your eye ignores. Now let's talk about the second feature, the total power radiated. This is where people start making mistakes because they think radiation is only something hot things do, like fire, metal, stars. But thermal radiation is a bookkeeping rule for energy. It happens at every temperature. The only question is how much and at what wavelengths. The simplest ideal rule is the Stefan-Boltzmann law. A perfect blackbody radiates power per unit area equal to Ceph T4, sigma times temperature to the fourth power. That fourth power is not a decoration, it's the reason a small increase in temperature can make a huge difference in radiated power. Now you are not a perfect blackbody. Real skin has an emissivity close to 1 in the thermal infrared, something like 0.95 to 0.99 depending on wavelength, moisture, hair, and so on, which means for infrared purposes you're almost a blackbody, you're a very good radiator, so we can actually estimate how much power you're dumping into the world as infrared light. Take a rough surface area for a human, around 1.7 square meters, depends on your size, but that's a decent number. Take your skin temperature, maybe 305 to 310 K at the surface, again depending on environment. If you pretend you're a perfect blackbody at 310 K, Cephas T4 is about 524 watts per square meter. Multiply by 1.7 square meters and you get around 900 watts. And people hear that and freak out. I'm emitting 900 watts, like a space heater. But wait, there is a catch. Always, you're also absorbing radiation from your surroundings. The walls, the furniture, the air, everything around you is also radiating infrared toward you. If the room is, say, 293 K, 20 degrees Celsius, then the room is radiating too. A perfect blackbody at 293 K radiates about 418 watts per square meter. So the net radiative heat loss is closer to the difference. Ses T body 4 mina T room 4 times area, with emissivity folded in. Do that and you get something like 150 to 200 watts of net radiative loss in a typical room. That's a much more reasonable number. It's in the same ballpark as human metabolic power at rest, around 80 to 100 watts, sometimes more, and your body balances it with a mix of radiation, convection, evaporation, and conduction. So you're not creating 900 watts of extra energy, you're participating in a constant exchange. A trade, photons leaving you, photons hitting you, and a net flow determined by temperature difference. That's thermal equilibrium trying to happen. And now we can say something sharper. A thermal camera does not detect heat, it detects infrared radiation. The photons, heat is energy in transit because of temperature difference. Radiation is one channel that heat can use. The camera is watching that channel. So if the camera sees you bright, it's because your skin is emitting more infrared power in that band than the background, or because the background is cooler, or because your emissivity is different, or all of those at once. Which brings up a subtle thing people don't realize. Thermal images are not pure temperature maps unless you know the emissivity of the surfaces. A shiny metal surface can look cold in a thermal camera even if it's not, because it's a poor emitter in infrared, and it reflects the infrared radiation of other objects like a mirror, but for heat light. That's why a crumpled piece of aluminum foil can look like it has weird patterns. You're seeing reflections of hot and cold things around it. Skin, cloth, painted walls, those are good emitters, so they behave closer to the ideal blackbody picture. They tell the truth more directly. Now I want you to picture the blackbody curve, not as a scary equation, but as a simple everyday object. Imagine a piano keyboard. Visible light is a tiny run of keys in the middle. Infrared is a huge stretch to the right. Ultraviolet to the left. Your eye can only hear a small octave in the middle. A thermal camera is listening to a different octave. The object, your body, is not playing a single note. It's playing a chord, a smeared out chord. Many frequencies at once, with a loudness pattern that depends on temperature. That's blackbody radiation. And as temperature rises, the chord shifts. It slides toward higher frequencies. That's why hot things eventually enter the visible octave. But unlike a piano where you choose the notes, matter doesn't choose. The distribution comes from the statistical motion of billions of charged particles jiggling around. Now if you want the photon picture, because the video is titled "You Are Glowing Right Now," not "You Are Exchanging Energy Continuously Through Thermodynamic Radiative Channels," we can translate power into photon count. At your peak wavelength around 10 micrometers, the frequency is about 310 hertz. The energy of one photon is E equals sign HF, which is roughly 610 4 times 310 about 2 px 10 quadro joules per photon. That is a tiny packet of energy, so if your net radiative output is, say, 150 watts, 150 joules per second, divide by 2 px 10 quadro joules per photon, and you get on the order of 10 quadrate photons per second, 10 billion trillion photons every second. That number is so stupidly large, it stops meaning anything. But it tells you one thing clearly: I am not emitting light is not even close to true.
You are emitting an outrageous number of photons. You are a photon sprinkler. Just not in the band your eye reports as light. And there's another twist here that people often miss.
You're not only emitting from your skin, you're also emitting from your breath. Warm, moist air, carbon dioxide, and water vapor, both of which have strong infrared absorption and emission features. That's why some thermal cameras can show a ghostly plume when you exhale. You're watching gases radiate because they're warm and because their molecules have vibrational modes that couple to infrared frequencies. So the glow is not a skin-deep trick. It's the entire warm molecular machine broadcasting. Now, why does any of this matter beyond party trivia? Because it fixes your definition of light. Light is not what I can see. That's a child's definition. Useful but wrong. Light is electromagnetic radiation, and once you accept that, the universe starts to look different. The room is not dark. It's filled with radiation. It's just radiation your eye can't register, and seeing becomes an engineering problem. What detector do you build? What wavelengths does it respond to? And what does the world look like through that window? That's what a thermal camera is, a different window. Not magic, not special vision, just a sensor that responds to photons you normally ignore. And there's one more problem we need to clear up before we go any further, because someone always says it. Okay, but if I'm emitting infrared photons, why can't I see them? Why didn't evolution give me infrared vision? Good question, but the answer isn't mystical. Infrared photons at room temperature carry less energy than visible photons. Detectors for them tend to be noisier because the detector itself is also warm and radiating in the same band. Your eyeball would be glowing in infrared too, blinding itself with its own thermal noise unless it were cooled. That's why serious infrared astronomy uses cooled detectors, sometimes very cold. So biology picked a band where the background isn't overwhelming and where sunlight is abundant. Visible light is a sweet spot, but physics doesn't care about sweet spots. Physics just says photons are being emitted constantly. And now that we've got the curve, the power, and the photon flood in our hands, we're ready for the next step. Why darkness is a human illusion, how temperature becomes a kind of color, and why the universe is basically forcing everything with temperature to leave a trail of light behind it, like a signature you can't turn off. So now we can close the loop on the original mistake. You said if I'm not visible in the dark, I'm not emitting light. What you actually meant was, if my eye can't detect photons in the 400-700 nanometer band coming from me, then I'm not emitting photons at all. And that leap is the whole illusion. Because dark is not a property of the room, it's a property of your detector. Darkness is what happens when the detector you're using isn't sensitive to the radiation that's present. Switch detectors and the world changes. Put on night vision goggles and the room becomes green and grainy because those devices amplify tiny amounts of visible and near-infrared light. Use a thermal camera and the room becomes a landscape of temperatures because now you're seeing mid-infrared radiation, your blackbody glow. Same reality, different slice. And once you accept that, a deeper idea becomes obvious. Light is not a special substance that only lamps and stars produce. Light is the way energy and information travel when charges jiggle, accelerate, or when quantum systems change state. Sometimes it's visible, often it isn't. You live your entire life inside an ocean of electromagnetic radiation, and your eyes are just one very narrow instrument for sampling it. Now I want to deal with one last mental snag people get stuck on. It sounds like this. Okay, I emit infrared photons, but is that really me glowing, or is it just heat? That question only exists because you were trained to separate light and heat like they're different categories of stuff. They're not. Heat is energy moving because of temperature difference. Radiation is one mechanism for moving that energy, and the radiation is made of photons. So when your body radiates heat, it does it by emitting light, infrared light. Heat radiation and infrared light are the same physical thing described in different moods. And if you want the cleanest, most honest statement, it's this. At any moment, your body is converting chemical energy from metabolism into a mixture of work, internal motion, and ultimately radiation. And some fraction of that leaves you as photons. Your glow is the universe's way of balancing the books. Now, step back and look at what that means in a human sense. You don't get to be off, even asleep, even in a sealed room, even in total darkness. You are radiating. The universe has a rule. If you have temperature, you broadcast. It's not a metaphor. It's a physical inevitability. Your atoms are in motion, and motion of charge couples to the electromagnetic field, and the field carries energy away. You are always leaving a trail, and it's not just you. Everything you think of as inert is doing it too. The desk, the wall, the cup, the floor. The reason you feel stable in the world is not because nothing is happening, it's because an enormous amount is happening in a way that averages out. Every object in this room is a little furnace of microscopic motion, continuously exchanging photons with everything else. So the room is not quiet, it's not empty, it's busy. If you could see infrared naturally, you would never experience darkness the way you do now. The whole world would be glowing all the time, different colors for different temperatures, moving patterns for convection, breath as a streaming ribbon, your own hands bright against cooler surfaces. And that's not sci-fi, that's physics plus a different detector. Now think about what that does to your definition of seeing. Seeing is not mystical, it's counting photons, it's detecting electromagnetic waves and building a picture. Your eye does it in one band, instruments do it everywhere else. A radio telescope sees the sky in radio. An X-ray detector sees through soft tissue because bones absorb differently. A thermal camera sees your glow because your skin is radiating in the infrared. So when someone calls thermal imaging magic, what they're really confessing is, I forgot my senses are not the universe. They're just one interface. And that's a good confession, because once you remember it, you start asking better questions. Not is there light, but what wavelengths are present. Not is the room empty, but what fields and radiation fill it. Not am I a thing sitting here, but what exchanges are happening between me and everything else. And here's where the existential part sneaks in, quietly, without philosophy. Your body stays warm because it is constantly burning fuel, food and oxygen, at a controlled rate. Life is not a static object, it's a process. If your metabolism stopped, your temperature would drift toward the room. Your glow would fade until you matched the environment, not because you turned off, but because the temperature difference disappeared. So your infrared glow is a signature of being out of equilibrium. Living things are little pockets of organized chemistry resisting equilibrium temporarily, and the cost of that resistance is energy flow outward, ultimately as heat, ultimately as photons. In a very literal sense, being alive means being a warm, structured pattern that can only persist by continuously dumping energy into the world, and the universe demands a receipt. That receipt is radiation. Now there's a beautiful twist in that, because it means your glow is not just waste, it's communication. You can measure it, you can infer temperature from it, you can detect a person at night from it. Animals do this. Some snakes have infrared sensitive pits that detect warm prey. They don't see you, they see your thermal signature against the background. They see your glow, so you are visible even in darkness, just not to the particular kind of eyes you happen to have. And that brings us to the clean payoff, the one sentence you should carry out of this. Light is not what you see, light is what exists. Visible light is just one narrow strip where your biology tuned itself. The universe is bigger than your strip. Right now, even if you're sitting perfectly still, you are emitting an enormous flood of photons into the room, mostly infrared, a little at other wavelengths. And the room is doing the same back to you. The universe keeps you on air. If you want a simple experiment to make this feel real, do this. Stand near a cold window on a winter night. You will feel colder even without touching it. Part of that is convection, sure, but part of it is radiative exchange. Your body is sending infrared to the window, and the window is sending less back because it's colder. You feel the net photon imbalance is cold. You are feeling light without seeing it. That's the point. And once you get comfortable with that, a lot of weird physics starts feeling less weird. It starts feeling honest. If you want more of this, more places where your intuition is confidently wrong, and the universe is doing something simpler and stranger underneath, subscribe, not for facts to memorize, for a different set of instincts. Because the more you understand what light really is, the harder it becomes to look at an ordinary dark room and call it empty,